Deja de ser engañado por Telcel y Telmex. Deja de pagar esas altísimas rentas mensuales. Con este dispositivo, no necesitas SIM ni contratos y tu mensualidad será de 0 pesos para siempre. Paga una vez y disfruta de internet satelital global gratis de por vida. Te presentamos el revolucionario Wi-Fi satelital portátil, desarrollado conjuntamente por la japonesa NTT y Starlink de Elon Musk para la gente como tú. Recibe la
Imagine being able to build an app.
The Black Lions too. Thank you. I will introduce first in Spanish and then we'll switch to English. ¿Cómo están todos? Muy buenos días. Gracias por estar aquí con nosotros. Yo quiero, primero que nada, agradecer en español y quiero sorprenderlos porque el profesor Ramakrishnan habla un poco de español, así que está entendiendo lo que decimos. Obviamente vamos a mantener la plática en inglés para darle fluidez, pero de verdad que quiero agradecer a toda esta comunidad, hacer sentir al profesor Ramakrishnan en casa. Ya le expliqué al profesor que somos una comunidad de líderes en investigación, en áreas básicas, en ingeniería, y que nuestros estudiantes tristemente son seleccionados y que tenemos a los mejores estudiantes de la región y que quisiéramos tenerlos a todos, pero que solo podemos tener algunos, ¿no? Yo voy a leer en español su currículum, luego vamos a cambiarnos a inglés, pero el formato que el profesor me ha pedido que tengamos esta plática es un diálogo. Él quiere tener un diálogo con ustedes. Platíquenme si sí tienen algunas tarjetas blancas que les repartieron. ¿Sí? Ah, perfecto. Eso es para que hagan sus preguntas y en un momento las depositamos y vamos a ir dándole lectura al mayor número de ellas, ¿no? Para darle agilidad, les voy a decir, el profesor Venki Ramakrishnan es un distinguido científico obvio de reconocimiento internacional, con aportes fundamentales para avanzar la biología molecular contemporánea. Él es físico de formación. You are a physicist.
Ahora no.
Sí. Después se especializó en biología estructural y tiene una trayectoria académica que lo ha hecho pasar por instituciones como la Universidad de Baroda o la Universidad de Ohio. En el 2009 fue galardonado con el Premio Nobel de Química junto con la doctora Ada Yonath y el doctor Thomas Stites por sus investigaciones de la estructura y el funcionamiento de los ribosomas, el complejo molecular responsable de sintetizar las proteínas en las células vivas. Su trabajo, que basó en técnicas avanzadas de cristalografía de rayos X, permitió describir con un detalle no antes visto la manera en que el ribosoma traduce la información genética, contribuyendo decisivamente a entender los procesos fundamentales de la vida. Este descubrimiento no nada más transformó la biología estructural, sino que también abrió la posibilidad de desarrollar nuevos antibióticos y desarrollar nuevas terapias génicas dirigidas a enfermedades específicas. El doctor Ramakrishnan es considerado una figura clave en la ciencia moderna y cuya labor continúa inspirando a nuevas generaciones en el ámbito, fíjense nada más, de la física, de la química, de la biología y por supuesto de la medicina. Les voy a pedir que recibamos con un caluroso aplauso al profesor Ramakrishnan. Welcome, Prof. We are so honored of welcoming you here in CUCEI. I forgot just to mention something. He works currently on the Cambridge biomolecular lab facility in there, and from there he's visiting today CUCEI. The first, Prof, we want to ask you just to open the dialogue, this dialogue, is, well, if you want to open with some remarks from you, we want to say salute to this community first.
No, why don't you go ahead?
Shall I?
Yeah.
Right, I'll then. Well, the first thing we want to ask you, because I know that's on the mind of many of the people working here today, you are a physicist himself.
I think no physicist would consider me a physicist.
And then
I only studied physics during my youth, and then in 1976, which is already, 50 years ago,
I know.
I left physics. And I have forgotten almost all my physics, so you have to think of me as a failed physicist, because if you gave me an exam in physics today, I would probably fail.
We know that you moved then to chemistry and then
biology.
to biology.
No, only to biology. This chemistry is a misunderstanding. You see, there is no Nobel Prize for biology.
I know.
So the Nobel Prize goes to either physiology or medicine, or if it is more biochemical or molecular, then it is given the chemistry prize. But there are many people who have won the Nobel Prize in chemistry who don't know any chemistry.
Actually,
Because
yeah.
they're biologists, they're molecular biologists and so on. And I know a little bit of chemistry, but I would not call myself a chemist, so I'm more of a molecular biologist.
No, actually, that gives us the first stint of the first question. With all your career and your trajectory, what's your opinion about, combining subjects for solving a problem? What's your advice for all the young students?
Many modern areas will require different techniques and different approaches. Even in biology, biologists are now using highly mathematical techniques, a lot of computational techniques, a lot of physical techniques. For example, in my field, I have used X-ray crystallography or electron microscopy. So these all are physical techniques. So underlying it, you have to know about electron optics and, something about Fourier transforms and so on. So there is this leakage of, techniques from one discipline to another. Now, at the same time, from the top, people are saying you should be multidisciplinary. Now, I think you cannot force that, okay? Some techniques, some research subjects will require multidisciplinary approaches. Others will not, and you will do brilliant work only in one discipline.
On the basics.
So I think science is diverse. There are many different kinds of science. Some will be multidisciplinary and some will not. What you have to do is to try to not erect barriers between the discipline so that you can make it easy for people to collaborate across disciplines. That's one thing, but the collaboration will be easier if everybody is trained broadly at the beginning so that you don't specialize too soon when you're being educated. Many countries, including Britain, they force you to go into a narrow discipline too early. Even in school, you have to choose between science and humanities. Mm-hmm. And then they choose between physical sciences and life sciences or medicine or something. So that kind of too much specialization early is not good, because then later on, if you have to collaborate, let's say you're a biologist, you have to collaborate with a physicist or engineer, but you don't know any physics or engineering or mathematics, then it's not easy to collaborate, right?
I know.
But if you have a fundamental foundation in all of the four, what I call core subjects, which is mathematics, physics, chemistry, and biology, then you can have a broad understanding of science, and you can then specialize later in life.
Believe me, Prof, that kind of advice is very important from us, from the educator side, because we need to decide on the future kind of programs for the degrees.
Yeah. So I would say, be as broad as you can for as long as possible. Ultimately, you then have to choose. You cannot study everything forever, right? So ultimately, you have to choose, but you can try and delay that choice until later.
Great. Actually, I was yesterday in your previous talk on the book fair, which, by the way, we need to also thank the International Guadalajara Book Fair this year for bringing Professor to this school. We are very thankful to the organization of the book fair, to Marisol Schultz, who is the director of this fair, for allow us to have you here, Prof. Well, I got a second question. We read in a lot of books, in your books, in news, on the newspaper, that most of your work has been focused on anti-aging, Prof. All the anti-aging.
Yeah, no, that's only this book.
I know.
Okay, so my research is really about how the body translates genetic information into proteins. So all of the proteins in our body, we have thousands of them, they're all made by translating genetic information. So each gene contains information for how to make a protein, and that process is done by copying that gene from DNA into a molecule called mRNA. Nobody had heard of mRNA 5 years ago, but now everybody has had mRNA in their arms because of the vaccine. Okay? But what the mRNA has are genetic instructions for how to make a protein, and that information is translated by a large complex called the ribosome. And that has been one of the main areas of my study. How does the ribosome work? How is it regulated? How do viruses hijack the ribosome to make its own proteins instead of the cell's proteins? How does it affect, how does the ribosome ensure quality of the protein, and so on. Now, this field is not about aging, but it is related to aging, because when we age, our ability to make proteins accurately and in the right amounts and with sufficient quality declines. And so a lot of the biology of aging has to do with protein synthesis and its regulation. So I don't work on aging per se myself, but I became interested because of many reasons. One is it's a big existential question, why we age and why we die. That's, humans have wondered about that for a long time. And another is that societies are getting older, and so there is a lot of interest in how to keep older people healthy. And a third reason is because of this enormous interest in aging, because of the aging population, there's a lot of money in aging. And also, the baby boomer generation is now getting old. They're worried about, reaching the end. And so they're extremely worried. And so this has resulted also in a lot of hype. And many scientists who work on aging also have a personal vested interest. They have a company, they're selling a particular kind of product, or they have a particular agenda. So I thought somebody like me who is not in the field, but very close to the field, could try to be more objective and write a book. So that explains my interest in aging.
Which, by the way, I had that yesterday in my hands. And there is another question many people asked me yesterday about your work. They said, what does it say in the book about this clock ticking, the ticking of the aging clock? Can you explain a little bit more about that?
Well, I wouldn't, aging is the result of damage to our systems, including especially starts at the molecular level, but then it manifests itself at the level of the cell and of our tissues and then our whole body. So this is the accumulation of damage and changes that occur with time. So as time passes, our DNA gets damaged, our cellular compartments get damaged, our cells themselves, lose many of their abilities and so on. So there's many different aspects of aging, but they all have to do with this accumulation of damage and changes that leads to a gradual loss of function over time. So that's really fundamentally what aging is about.
About this damaging of tissues, cells. And
yeah.
Right. Prof, we got my final question, because it would be a good time for everyone to ask you different sorts of things from the student point of view, from the professors, from the researchers too. Have you considered any of the social or psychological consequences of making the people live longer than we live today?
Right. So there are two parts to this question. One is, if you ask most of the researchers in the longevity research community, they will say they don't want to extend life. They want to extend health. So they want people to live healthy for a longer time so that they're healthy in old age, they don't have all of the, disabilities of old age. But my worry is that if you improve your health in old age, you will also extend life. So, and you may simply postpone that period when you are not very healthy. So that, it's not entirely clear. But let's suppose that they actually do improve health, and as a result, they also improve lifespan, increase lifespan. Then we will have a society where people are living longer. Maybe far more people will live to be 100, let us say, as a result of anti-aging advances. And at the same time, we have a huge drop in fertility. Fewer and fewer in most societies, fewer and fewer people are having children, or at least fewer children are being born. And in many countries, the birth rate is below the replacement rate. In fact, the only reason some countries sustain their population is by immigration, which Mr. Trump doesn't understand. But
by the way,
but the fact is that if you have a society with very, very slow change, very few people being born and people living for a very long time, it will have social consequences. It will increase economic disparity because rich people tend to live longer because they have better access to better nutrition, better health care, less stress, etc. And also there'll be intergenerational disparities because older people are not dying off, but they're hanging around, they're richer and more powerful as they get older. And so younger people will have to sort of, enter this world where maybe opportunities won't exist for them as much as they would if in a society with a lot of turnover. So I do think, that we're not completely appreciating that the consequences for society. In fact, we don't know what the consequences will be. Maybe it won't be so bad, but maybe it could be a real problem.
At the end.
Yeah.
We'll see. Thank you, Prof. And here we got the first generation of questions from our auditorium now. We got the students and professors. Let's do one on one, if you agree with that.
You can censor them.
Okay, we'll do. I suppose they do some kind of assortment now, but I'll see. Well, this is from Daniela Villaseñor from Ingeniería Industrial. Where are you, Daniela? Just to make sure you are not AI agents. Thank you. Oh, this is in Spanish. Which is the most important challenge from a scientific point of view that you face when you were trying to develop this structure, the atomic structure of the ribosome, and which this breakthrough was the most surprising one for you during the whole process of describing the ribosome? Which is a good question. Thank you, Daniela.
Yeah. No, I think the biggest problem there were two big problems. One is when we started, we were using a technique called X-ray crystallography to determine the structure of the ribosome. And for this method, you need to get good crystals of the ribosome. And there had been good crystals of the large subunit, which had been discovered by Ada Jonat, but nobody had yet solved them. Even though the crystals were there, nobody had actually figured out how to solve a structure. But there were no good crystals of the small subunit, which we started to work on, or the entire ribosome. So the ribosome has two parts, a large part and a small part. And then there's the whole ribosome, which is the two parts put together. So we started working on it, and we didn't know whether we could get crystals that were of sufficiently good quality. Now, crystallizing something small like salt or sugar is very simple. You make a solution and you simply let it evaporate and you'll get crystals. And any school child knows how to get crystals of salt or sugar. But when you have a large, complicated molecule with hundreds of thousands of atoms, that molecule is very floppy. It's not extremely rigid, and it can only assemble as a crystal in certain ways. And it's not easy to get crystals. So that was one big step. Then the next big step was to see if our ideas of how to solve it would work. And that requires these very powerful X-ray sources called synchrotrons, which are essentially big accelerators, electron accelerators, which emit very powerful beams of X-rays. Because these crystals of ribosomes are very small. And so to get enough signal, you have to hit them very hard with very powerful X-rays. So that was a second challenge. And I think the big breakthrough was when we finished our experiment, we could actually see parts of the ribosome that we could recognize, like a double helix of RNA, which is similar to a double helix of DNA. It's like what's called an A form DNA, not the traditional B form. But we could see this RNA double helix, and so we knew that the experiment was working. And so that moment when you can see something that was not seen before, that was for us the big breakthrough.
It's difficult for anyone to imagine how a synchrotron will have to do something with biology, isn't it?
Some of the biggest users of synchrotrons have been biologists. In fact, I would say in terms of publications and time, maybe half of all synchrotron uses or more has been for biology.
Biologists themselves. Wow. Well, this question comes from Azucena. He's a professor from the Department of Chemical Engineering. Where are you, Azucena? Azucena, I'll see you, Prof. Azucena, thank you. Which was the thing that most inspired you to change from physics to biology, to molecular biology?
Yeah, so there were two. There's a kind of push factor and a pull factor, okay? So the push factor is I was working, I did okay on my exams. I didn't have big problems taking physics exams, even in graduate school. I could take exams and do okay in them. But once I started doing research, I found it very difficult because I couldn't get a sense of what is the problem, what is the question you want to answer. And I was also doing theory. I was not doing experimental physics. I was doing theoretical condensed matter physics. And I had no real feel for it. And I have to say, after a year, I was very frustrated and quite bored, and also, finding it very difficult. And so I was reading articles in Scientific American and other popular magazines, and it seemed like biology was undergoing a huge revolution. People had figured out how to sequence DNA for the first time. For the first time, they had visualized what biological molecules look like. They had figured out a lot about the immune system. They had figured out, what a cellular architecture was like. All sorts of very, very fundamental breakthroughs were being made in biology. And so it seemed to me that maybe that was an exciting field. Now, it also turned out that many physicists had already made this transition before. For example, Francis Crick, who was one of the co-discoverers of the structure of DNA, started as a physicist. Max Delbruck, who won the Nobel Prize for phage genetics, for bacteriophages, which are viruses, and how and their genetics. He was also started life as a physicist. So I thought, okay, there are physicists who have made this transition. And so I didn't know any biology, so I didn't want to work as a postdoc. In fact, I was offered a couple of postdocs at Yale, one by Thomas Stites, with whom I ended up sharing the Nobel Prize, some 35 years later. And I told both of them, I'm not ready for a postdoc. And instead I went to University of California in San Diego to become a graduate student all over again in biology. And the first year, I didn't understand any biology, so I even took undergraduate courses to make up my background. So the first year, I was taking only undergraduate courses and doing some practical lab work. And then in the second year, I started doing some real biological research. So that was how I made that transition.
Wow, thank you, Prof. Now we got another question from a professor here, Antonio Casillas. Raise your hands, Dr. Antonio. It's actually English, thank you. From someone as you, whose work has profoundly changed our understanding of life's fundamental machinery, there are two questions. The first one is, what's your biggest concerns about the current direction of global scientific research? And conversely, what is the most appropriate hope for the future in scientific work on in this direction?
Well, I think one concern is that maybe it has always been true that science, the progress of science, has been extremely unevenly distributed. For example, in the 17th, 18th, and 19th century, nearly all of the big scientific progress came out of Europe, and especially Northern Europe, because Southern Europe, for various, political and social reasons, after Galileo made big advances, it really lost the edge in science, and the focus shifted to Northern Europe. And then, in the 20th century, it shifted to America, especially after the 1930s or so. But even in America, science is not evenly distributed. It is, highly concentrated in the Northeast, in California, to some extent the Northwest, a few places in the Midwest. These are where a lot of the science is being done. And so this is leading to a kind of polarization in scientific progress. And I think that's, and especially since we're here in Mexico, it's an important thing. How, and it's same with countries like India. How do they compete, in a world where there's this kind of concentration of science? But the fact that, East Asia, like China, Japan, Korea, Taiwan, and Singapore also, they have really advanced dramatically in science. So 40 years ago, they were nowhere, okay? Mm-hmm. And now they're among the world leaders in science. So that shows it's possible to do possible. That. Okay, so that is one worry. The other worry is that science may not always be used for the benefit of everyone, And this will happen if more and more science is done not in academic institutions, but in private corporations with their own agendas.
Profit.
And that is happening even in the aging field, for example. Mm-hmm. A big lab, Altos Labs, opened up, which is funded by a bunch of tech billionaires. And they opened up 2 campuses in California and one near where I live in Cambridge. Mm-hmm. And in the process, they basically took lots of top scientists from top universities, Stanford and UCLA and the Salk Institute, Cambridge University, etc. And they're all now working for Altos Labs. But Altos Labs is a private business, So, how does this, how does this work, and what's going to be the result of it all? It's not clear. I'm not against private enterprise because many of our technology, many of our medicines all come from private enterprise. So you need both. But if you have too much concentration in private, business hands, concentration of knowledge, then I do wonder about what it will mean for society.
I know. Well, thank you, Prof. Well, we got another Nice question from Ashley Velasquez from the chemical department. Where are you? The chemistry department. Where are you, Ashley? Raise your hand. Where are you? Ah, thank you, Ashley. She's there. And what was the hardest mindset shift you had to make in order to apply your understanding of molecular biology to questions about longevity?
What was the, sorry?
The hardest mindset shift you have to make in order to
I don't think it was very different because, you know, fundamentally, at some level, all of aging is really molecular biology in action, okay? Because ultimately, everything in life is molecular, and then it has its manifestations at more and more higher levels of complexity. So it didn't require really any shift at all. It simply required reading a lot and talking to people in the field and reading some of the papers with a very critical eye. I think that's really what it took. So it took a lot of work, but I don't think it took a mind shift. Yeah.
Right. This comes from Paulina Garcia from Industrial Engineer. Where are you, Paulina? Paulina Garcia? Oh, just down in the back. Thank you. That's an advice for youngsters. She says, what's your advice about how to choose a real scientific problem to be solved? How they used to say difficult but feasible to solve, just like the ribosome was decades ago.
Yeah, so this is an incredibly important question for which there's no really good answer, okay? So if you take the ribosome, when I started working on the ribosome in 1978, the idea that we would solve the whole ribosome structure was just a dream. So we were not, I didn't go into it saying, okay, we're going to solve the structure of the ribosome. We thought, well, let us understand the ribosome. Let us figure out if we can do experiments that tell us something about the ribosome, maybe a little bit about parts of its structure, maybe a little bit about its organization, and so on. So I think what you have to ask, my view is a good way to do, what 90% of scientists do is they don't think about the big question that they're trying to answer. They simply think, okay, I've done this experiment, what's the next experiment I can do? Okay, and it's not leading towards something. And so at the end of their career, they may have published, you know, lots of papers, but in the end it has not actually amounted to a lot. Okay, it's just a lot of papers. On the other hand, if you choose a big, important question, you cannot solve it right away. So what you have to figure out is, that's the question. Imagine you have to climb to the top of Mount Everest. You cannot go there in one step. You have to figure out, if I want to get to the top of Everest, where do I have to start? And how do I have to go? And where do I have to set up base camp? What's the next step? What are the dangerous points, etc.? So it's the same way with a scientific question. You should think of a question that interests you. You know, it could be a very broad question. And then you could ask, okay, what can I do now that will get me a little bit closer to that question? And you have to be able to break it into small steps that you can show progress and you can publish, because nobody is going to support you for 20 years with no results, right? So you have to have small incremental steps. But you have to keep that goal in mind so that you're working towards that goal. And that way, I think, you know, at the end of a career, you will say, okay, maybe I didn't get to the goal, but I really, you know, made a lot of advances that maybe future scientists can build on. So I think that's a slightly different way to do science. And I have to say, I didn't have that. I was just like everybody else, but then I went on sabbatical to the MRC lab of molecular biology in Cambridge. And there I realized that all the people there were working on really important questions. Nobody was there doing something kind of trivial or obvious. And they didn't care how long it would take. They would just do the next thing that would get them closer to that problem. So I felt, that was a better way to do science, and that would be my suggestion.
Thank you. Actually, we got another similar question from Professor Luis Javier Gonzalez. Where are you? One of my friends. I just there.
Oh, by the way, one thing I wanted to say is, there's always a question of, is this problem doable? Is it feasible now, or is it premature? And also, am I using the right approach, or am I, using an approach that's not likely to work out? And should I try a different approach? Those are problems that scientists face every day, and you only get an idea of how to do that with experience. And this is where mentorship helps. If you have good mentors who have a lot of experience in doing really good science themselves, they can give you feedback, whether you're working on the right problem, whether you're using the right approach or not. Okay, because some problems are important, but they may be not doable today because we don't have the tools or the understanding, to tackle them.
Or the appropriate approach to get them, isn't it? Right, this professor asks you, maybe that's the same question, but still, what would be your best advice for young researchers just coming into research?
Yeah, so, that was one advice, but the other advice was related to an earlier question, which is, don't specialize too soon. Try to get a broad education early in life, and then use that broad education to specialize.
Thank you, Prof. Right, this is come from a student, Lisbeth Magaña. Where are you? Lisbeth Magaña from Chemical Engineering. Where are you? No? It's not. It's there. Just say hello. Just behind the screen there. What's the best thing of winning the Nobel Prize? What's the best?
Well, first of all, there's a lot of money associated, especially especially if you're a scientist working in Britain. It makes a big difference. I was able to pay off my mortgage, and I bought my son a cello, because he's a professional cellist. So that was one advantage. I think the big advantage is that it gives you a voice. Of course, you can also misuse the Nobel Prize because people misunderstand what it means to be a Nobel laureate, because they think because you're a Nobel laureate, you're some sort of genius, you know everything about everything. But it's not true. Many scientists have won the Nobel Prize, they're not even that smart, but they happen to be lucky and made an important discovery. Other people have simply been well-trained and in the right place at the right time, and they've done very good work. But it doesn't mean they know very much outside their field. Outside their field, they're not experts, okay? And so people start treating you like you're some sort of prophet. And that's a danger, okay? On the other hand, though, it gives you some credibility. For example, when I was president of the Royal Society, which is the Academy for Sciences in Britain, and it's one of the oldest science academies in the world, I had to constantly talk with government, especially after Brexit. We had to convince the British government to adopt certain policies for science. And the fact that you have a Nobel Prize gives you some credibility. So they feel, oh, this person has done important work, he's well recognized, at least his fellow scientists think well of him. So they treat you with a bit of respect. So you can use that prize to do some good for science, so that's something you can do.
Interesting, thank you, Prof. Now we got a question from Carlos Mora from Chemical Engineering. Carlos, where are you, Carlos Mora? He's just there, just behind the screen too. Wow. We'll choose from another different place now. Even we are in the presence of a brilliant person just like you. That where were those things that you struggled the most along your career? even not having enough knowledge about your one subject, do you ever feel tired or uncertain about something or some things or going on ahead with your research? He's asking that.
Oh, well, life, in research is full of frustrations because 95% of the time, maybe even higher, nothing is working, okay? And the reason is that as soon as something works, you publish the results, and then you move on to the next problem, and again, nothing is working. So you have to face a life where things are simply not working, and you have to try to get them to work. And that can be quite challenging. And sometimes you're trying various things and nothing is working, you don't know what to try next, and you're depressed, and so on. So my advice is that science is more like a marathon, not like a sprint, okay? And so it's not a 100-meter dash, it's more like a marathon. And so you have to pace yourself, and you also have to have other things in your life. You have to have social life, you have to have hobbies, maybe you exercise or go for walks or go to the movies or whatever, so you have to step aside. Maybe you like music or you like theater, whatever you enjoy. You have to enjoy things, and you have to enjoy the process of science. You have to like coming in every day and doing experiments or doing calculations or whatever, because you're going to say, okay, at the end of the day, I will know a little bit more than I did when I started. So you have to enjoy the process. That would be my advice. If you don't enjoy the process and you don't have a kind of interest in your goals, then that would be like me doing physics, better to leave and do something else.
Actually, Prof, we got a question from Veronica Mendoza, who is a physicist herself. Where are you, Veronica? Just there. And the question is very nice. She wants to ask you about your perception of the intrinsic meaning of life, death, and its purpose in general from a philosophical or scientific point of view. Life and death.
The meaning of life?
And death as well, yeah. And she says, finally, all his respects to you, and thank you for coming to my school. Thank you. Thank you, Veronica.
This is what I was talking about, that people assume that Nobel laureates are prophets. So they will ask them about the meaning of life, I don't know the meaning of life. I don't think life has a meaning, actually. Life has only the meaning that you give to it, so it means whatever you want to give to it, and for different people it'll be different things. For some people their work is their passion, for others it is their family, for others it is maybe their hobbies or their other interests. So I think there's no I don't think there's a standard answer to that.
Right, thank you, Prof. This comes from a professor, Jose Luis Romero. Where are you? Just there in the corner. As much as people know about biology, do you think there is a revival of the mechanism, just something similar to what happened during the illustration in the middle time of
what happened to what?
To the mechanism, I suppose the application of physical principles to biology, mechanization or things.
I didn't understand the question.
Way that the illustration, do you remember the French illustration after the medieval times, that everything changed in science?
Yeah.
I think he meant that, the illustration.
Well, can I see this?
Yes, of course. It's a difficult, quite an abstract question, yeah. Would you like to explain more, Jose Luis?
No.
Come forward, explain more about the question.
I sort of understand. So the question is, ultimately, biology at the fundamental level is chemistry in action, okay? Because everything in biology is the result of molecular interactions, and therefore it's chemical interactions and chemical reactions that are determining what the outcome is biologically. And of course, chemistry you can think of as essentially, physics that is applied at the atomic level and the molecular level. So it's atomic and molecular physics is really what chemistry is. So there's a kind of hierarchy, but it doesn't mean that you can solve the Schrodinger equation for the cell, okay? Knowing that underlying it is physical laws and then laws of chemistry doesn't help you understand biology directly. So it's not a reductionist subject in that sense, like physics, many areas of physics are. And so if you have to ask what is the one fundamental principle in biology, it's evolution, okay, by natural selection. And so that principle really explains how life has the form and the diversity that it has today. So that would be the one fundamental principle.
Great. I'd like to say thank you to Jorge Hernandez, to Andres and Jorge Mendoza, which your questions are being answered now, I think. That's why I just passed them over. We got another one from Mario de Lopez Aguiñaga. Where are you? From the PhD on computational intelligence. He asked you, when you were learning about tackling complex problems and abstract objectives, what was your main challenge, tackling abstract problems, complex problems, where you were facing them? What was your main?
Well, I think, well, first of all, my problem may have been complex, but it was not abstract, okay? I mean, what I was, when I was trying to do physics, that was much more abstract than, say, solving the structure of the ribosome, which was a complicated problem, but it was very, very, very visual, and the methods were, sort of straightforward. But it was really a question of how to get them to work. I think, there are a number of issues in science. One is you have to have the resources, you have to have the money, you have to have the people to do it, the people have to have the expertise, or you have to train them, you have to have the equipment and the laboratory to carry out the experiments, you have to be able to go to synchrotrons to collect data. So it requires this big experimental infrastructure in order to be able to do what I did. Now, different kinds of science require different infrastructures. There are some kinds of science where you can do very clever and informative experiments with very little equipment, and people have done that. And so that's also possible, and that requires, a different kind of problem and different kind of approach. So I think the difficulties are different for everyone. It depends on the problem.
I want to leave you this one for reading by yourself, because it's quite a personal question. It's come from Professor Omar. Where are you?
Well, yes, what am I going to do now that I'm retiring? So I don't really know. I mean, I'm involved, I have a number of things that I'm involved with. For example, I'm a consultant for some biotech companies. I also helped co-found a company that is trying to use RNA for therapeutics. So that's taking up a fair amount of my interest now. And this is a nice thing because, I can apply 40 years of research and my background to try to do something that might improve human health. Okay, so it's a different kind of adventure. And then I've written 2 popular books, so I may think about taking up science writing, as another occupation. So it's a kind of, I only retired last month, and maybe I should have thought about it a long time ago, but I thought, well, there's no hurry. Once I retire, it's not like I have a deadline and I have to decide what to do. So I may take some time in the next year to think about what I want to do. And one thing that will amuse some of the physics professors is that I thought it would be interesting to go back and relearn some of the physics that I forgot, and then also learn some new things about physics, because there are all these areas like quantum entanglement and quantum computing, which I read about but I don't really understand. And so I thought maybe if I relearn some physics, I can maybe understand that. So again, you can't do everything, so I will have to focus on something.
Believe me, Prof, that will be music from the ears of many physicists there. They are glad of hearing that. I got another question from Natalie Padilla from the Chemical Engineering degree. Where are you, Natalie? Natalie Padilla, just there. It's a beautiful question. And it's actually a question of a question. What question do you think the scientific community is not asking yet, but must be asking themselves?
Oh, I think that's extremely hard to say. It's a very good question. But I have to say, Feynman, Richard Feynman, the famous physicist, was once asked, so what is the next big question in physics? And Feynman replied, if I knew that, I would be working on it. So I think it's a little bit like that. I don't know what you're asking, what is the unknown? What is the thing that we don't know or that we're not asking? And I just don't know. That's the simple answer.
Thank you, Prof. I shall thank you, Jocelyn Silva and Karen from physics. Your questions, they've been answered now, I suppose. Now we got, wow. This comes from Marta Reyes from La Paz, Baja California. Thank you, Marta. There is a beautiful and personal question. She says, my little daughter asked me, 14 years old she is, Mama, what do you need to win a Nobel Prize? What must be the goal for winning a Nobel Prize? Shall I work hard? Shall I have perseverance on that? What's your advice on the point?
My advice would be not to forget about the Nobel Prize, because when we are like teenagers, when we're 15 or 16 and we think of doing science, we think, oh, I'll do science and maybe one day I'll win the Nobel Prize, But by the time you're in graduate school, you realize that the chances of winning a Nobel Prize are extremely small. You can be doing very important work and publishing in top journals and still not be an actual contender for the Nobel Prize. I would say a better approach is to work on something that you find really fascinating and interesting, and that will the topic will keep you motivated. If you think of the Nobel Prize, you will only have frustration. But if you're working on an interesting problem, you will be enjoying your career and your life as a scientist because you're interested in your work. And paradoxically, that is probably the best way to get a Nobel Prize, because if you work on something that you care about, that you think is very important and interesting, the chances are you will do your best work, and that will give you the best chances. But I would say the Nobel Prize is a little bit like winning a lottery ticket. There are so many important discoveries, but they can only give one Nobel Prize every year in each field. And so you have to be one of 3 people in that particular field. So it's a little bit of a lottery ticket. I wouldn't, you wouldn't advise somebody to buy lottery tickets as a career, right? So it's the same thing.
Thank you to Adriana Ramirez and Gonzalo Padilla from Chemical Engineering. I think your question was answered now. We got another one from Harold Perez Ramos. Where are you, Harold? Thank you. Oh, thank you, guys. What was the most important breakthrough after you discovered all the structure of the ribosome? What was the most important from your point of view?
I think, two things came out of the structure. The first thing is that once we had the structure of the ribosome, you could immediately solve the structures of lots of antibiotics bound to the ribosome. So many clinically important antibiotics like erythromycin, tetracycline, streptomycin, all of these bind to the ribosome, and so you can figure out exactly how they work. And so that was one important thing. The other was that the first structures of the ribosome were just the beginning. the ribosome is like a complicated machine. So you have to, trap the ribosome in different states and try to understand how it goes from the beginning to the end in the process of making a protein. And that took many years. It's still not finished, actually. And another big advance was that we were using X-ray crystallography, which is a very slow and tedious procedure, partly because it's so difficult to get crystals. But now there is a technique called cryo-electron microscopy, which won the 2017 Nobel Prize. And actually, one of my colleagues was one of the winners of that prize. And that technique now allows you to solve complicated molecular structures much more easily. And then recently, there are computational methods using machine learning that can allow you to even predict structures, not complicated ones like the ribosome, but certainly structures of smaller proteins and protein complexes can be predicted using these AI-related, machine learning-related methods. So there have been a lot of advances which allow us to tackle more and more complicated questions in molecular biology.
And actually, it comes from this very handy question. Adrián Mancera, where are you, Adrián Mancera, from Chemical Engineering, in the current panorama of all the science and scientific breakthroughs, what's your opinion about the best area of study with more opportunities for new advances in the future? Good question.
I
Thank
think,
you.
This is, again, it's a very subjective question because, if you say, if you had asked somebody 5 or 10 years ago, what's a great area of progress? You would say, go into computer science because it's taking off and, there'll be a huge number of jobs. Now I read in the newspapers that, computer science graduates are finding it hard to get jobs because a lot of entry-level jobs in computer science are being done by AI, a lot of entry-level coding. So I don't know what to say. So I would say, it's a little bit like financial investing, okay? If you go to a financial investor and you say, tell me what stock I should buy that will make me, a lot of money 10 years down, they will say, no, that's the wrong approach, okay? They will tell you, you need to diversify your portfolio. So you should not, put all your bets on one thing. So I would say, again, I go back to my original thing, which is get a broad education early in life, and then try to specialize in something you're interested in. If it doesn't work out and you have to change, which will happen all the time now because science is changing so rapidly that so you may be in a field and that field may, eventually not be that useful. But if you have a broad education, even in biology, if you have a broad education, but let's say earlier on you have an even broader education, then you're able to shift quite easily from one field to another, depending on how things change. So that would be my advice rather than, it's not possible to really predict. It's like asking someone to pick a stock, okay? And that's very difficult.
Thank you, Prof. We don't want to get you so tired of talking to us. We will have 2 last questions this afternoon. But before that, I'd like to say thank you to the masters, to the students of the Master of Science on Chemistry. Where are you? All the students from, thank you. I think your question has been answered now, isn't it? Thank you. Thank you, guys. And the last 2 questions, this comes from Leslie Quintana from the chemistry program. Thank you, Leslie. Looking back at your career as a researcher, what was the most significant obstacle you faced in your research journey?
Well, I would say the worst moment in my career was after I did my postdoctoral fellowship. So you remember, I had a very strange career. I was a physics student, first in India and then at a university in Ohio. Then I studied biology for 2 years in San Diego. Then I went to Yale University for a postdoc. And in Yale, I was working on the ribosome. At that time, the ribosome was already not fashionable anymore. And I was using a somewhat strange technique, which most biochemists didn't really understand, and it turned out to be not a very useful technique. So when I applied after my postdoc for faculty positions, I think I submitted maybe 50 applications to all ranges, from teaching colleges to, lesser second-tier research universities to more advanced universities. And I got no interviews at all, zero, okay? And I didn't know, I thought, okay, first I failed in physics, now I'm failing in biology, And so it was like, I was thinking nothing is working out for me. And then eventually, I got a job, and then that turned out to be not a very good job. And then I had to switch to another job in a national lab on Long Island called Brookhaven National Lab. And that allowed me to slowly develop my career. And that also turned out to be kind of a dead end. And then I went on my sabbatical to Cambridge, and that really changed my life as a scientist. So I would say there were a number of times when I felt that my career was not going to work out. So I had all kinds of backup plans. So, this was in the 70s and early 80s. Now every school child knows how to program, but at that time, computer programming was still a useful skill that you could get a job with. So I thought maybe I would go to Silicon Valley and work for a computer company. Maybe I would have been an extremely rich person today, if I had done that. And the other thing I thought was, okay, colleges and universities don't want me, but maybe I could teach science or mathematics in high school, And I thought that maybe I would have to get maybe 1 year of training, and then I could teach in high school. And I thought that would be quite a good job, because you're training the next generation of citizens and potential scientists. So I always had these backup plans in mind when things were not straightforward.
Thank you, Prof. Now the least but not last question. What ethical challenges do you consider might arise if we significantly extend the human lifespan?
Well, there are a number of challenges. One is, if you have a society where people keep living for a long time, there are two issues. One is, how do you ensure intergenerational fairness? What happens to the young people if old people continue on in their jobs and don't retire and keep working? That's one problem. The other problem is, as people get older and if they continue to live and are reasonably healthy, what is society going to do with them? How will they, be integrated into society in a way that is good for both them and for society? So I think there are a number of really big questions that I think all societies are grappling with this. And of course, there's a lot of, as people get older and societies get older, there's a lot of movement about ageism. So they think of ageism as a prejudice, like racism or sexism. But the problem with that is we do decline as we get older. It's a real fact. Okay, I am not as, I don't run as fast as I used to when I was 20, and I'm sure that I don't think as quickly as I did when I was 20 also. And so, the question is, in spite of all that, how can you ensure that older people have a useful and welcome role in society while preserving opportunities for younger people? I think this is going to be a tricky balance, and all countries in the world are going to face it. And the only places where the population is still growing rapidly is sub-Saharan Africa, but even there, the trends are that the population rate is going to go down, the growth rate is going to go down.
Excellent, thank you very much. That was a question from Oscar Javier Leon. Where are you, Oscar? Oh, thank you. That was your question. And I promise that was the last one, but you know, there is a guy who comes all the way from La Paz, Baja California, near to San Diego. Well, at the end of the peninsula. And I want to honor his whole journey. Where are you, Carlos Angulo from La Paz? Where are you, Carlos? Oh, thank you for the question. He came over just to being here, Prof, and he wants your advice on how scientists must communicate the science to all the society in general. How can that be?
That's a hard question, and I would the first thing I would say is don't force scientists to communicate to the public, because many scientists are useless at communicating. You know, they simply don't know how to communicate, because to communicate you have to imagine yourself as not knowing anything, and ask what would it be like to receive this information. You have to put yourself in the mind of the reader. And many scientists are not able to do that. They're not even able to communicate outside their own discipline, okay, let alone to the general public. But you have to encourage it. So you have to encourage scientists to talk to, some scientists are good communicators, so you have to encourage them to take the time to communicate. Others you have to encourage to talk to science communicators, and there can be a dialogue between the science communicator and the scientist, out of which some, way of transmitting information can come. And the reason I think it's very important is for two reasons. One is a lot of science is funded by taxpayers, so it's very important for the public to know what is being done with their taxes. Okay, what are scientists doing with their taxes? The other is a more philosophical thing. Science is really dramatically changing our understanding of the world and the universe, and it's very exciting. And it's important to convey that excitement to the public. It's as much a part of human culture as literature or music or art. Our knowledge of the world and the universe, it's as much a part of our culture. So I think that's very important. And the other is that we live in an increasingly scientific and technological society, and all kinds of decisions are being made. For example, should we modify genomes? Should you have genetically modified crops? Should we use AI for say, job applicants, or for, calculating, medical interventions? These are all technical questions, and if the public doesn't understand the basis of it, then that's not necessarily a good thing for society. So I think a well-informed public is very, very important as we go forward in the 21st century.
Excellent. Well, Prof, we want to thank you for all this long conversation. That was very useful. And thank you to all of our students and professors and community in general, visitors. I hope you feel at home hearing CUCEI. That was the whole purpose of your visit here. I like to make some announcements here. The professor's editor or publisher is the editorial Grano de Sal. They are with us this morning. I shall thank you for that. Thank you, guys. They are just there in this table down the corridor. And they are selling the books. And Professor will take some minutes to sign some of the books if you want to buy the book and have that signed by the professor. That would be our honor to be here with you. We got two titles, The Genetics Machinery, which is very famous actually, and the most famous, I think, Why We Die, isn't it? That's the most famous book of Professor Ramakrishnan. And before that, Prof, I'd like to give you something to take away from you, from here, from CUCEI. Just a very simple present. Thank you. This is just with our heartfelt thank you to you from this community. And thank you for visiting us this morning, Prof. Thank you. Thank you very much. Oh, we already got a queue there, Prof. Waiting for the signature. A table will come in a minute here. If you want, bring the table here, guys. Bring the table. Bring the table here, yeah. Oh, that would be nicer if we, yeah, it's very easy. Ah, he's there? Well, that it's completely open now. Wow, these guys are fast. And thank you, Prof. I hope you will enjoy talking to our community. Wow, that was fast. Thank you. Thank you very much. I think we shall put this a little bit closer to us, Prof, just to make sure we got enough space for the people coming in. Sorry. Oops. That's it, I think. That will do, guys. Thank you very much for being here to all of you, and thanks, Prof, for being here this morning.